By investigating the Earth's crust and nearby planets, scientists believe the Earth is 4.54 billion years old. The Earth's core, the innermost center of the Earth, is assessed to be younger than our planet at 1 billion years old. Made of mostly iron and nickel, the Earth's core is located 1,802 miles beneath the Earth's surface and is suspected to be about the same temperature as the Sun's surface at 9,800 degrees Fahrenheit. Taking into consideration the depth and temperature of the Earth's core, how deep could we possibly dig into the Earth? The deepest anyone has ever achieved drilling into the Earth is 7.6 miles below, which is 0.2% of the way to the core. The Earth is made up of 4 different layers. From the outside going in, the top layer is the crust, then the mantle, the outer core, and the inner core. Each layer has its own distinct characteristics, physical state, and chemical composition. The inner core is younger than the rest of the planet we live on because after 500 million years of the Earth's existence, the collision and compression at the center of what is a ball of hot rock reached the melting point of iron at 2,800 degrees Fahrenheit. The Earth's crust is roughly 30 miles in depth and increases in temperature by 77 degrees Fahrenheit every 0.6 miles down into the Earth. By the time we reach the mantle, the temperatures are estimated to reach between 1,200 to 2,200 degrees. Let's take a closer look at each layer of the Earth to help determine how deep we may feasibly be able to burrow into the Earth. The Earth's crust. The Earth's crust is the thinnest and outermost layer. We live our lives on the Earth's crust and is the layer we are familiar with and the one we know the most about. Only about 30 miles into the Earth and at 1% of the Earth's mass, the crust was formed 4.5 billion years ago and is made up of granite and basalt rocks. The ocean floor crust is made up of basalt rocks, which is a volcanic rock, and the crust of land is primarily granite. There are different theories on how the Earth's crust was formed. The most widely believed theory is that the Earth's crust was formed during accretion, which is a process similar to a snowball rolling down a hill, which grows while accumulating more parts. The heavier materials dropped, and the lighter materials rose. The heat at the center melted the early mantle. As the mantle cooled, the lighter matter became the Earth's crust. Another theory is that the mantle traveled up to the Earth's surface, cooled, and designed the crust. Oceanic crust. The ocean's crust is younger than the continental crust and is about 270 million years old. This is due to a process within the lithosphere, which is the point on the Earth where the crust meets the mantle. Plates drift on the liquid mantle, and when a dense oceanic plate meets with another plate, called tectonic plates, the heavier ocean floor sinks into the mantle. This is called subduction and is the reason why the ocean floor is younger. The plate motions create mid-ocean ridges where new and hot oceanic crust is formed. Subduction in the oceanic lithosphere creates a recycling of the oceanic crust, which does not exist in the continental lithosphere. Some continental crust rocks and minerals date back to over 4 billion years ago, as opposed to millions of years ago found on the ocean floor. The oceanic crust is about 4 miles down, so it is not as far from the center of the Earth as the continental crust. Would it be easier to dig further into the Earth through the oceanic crust? Continental crust. The continental crust is mostly made of granite. It is deeper than the basalt floor of the oceanic crust, going about 44 miles down. The matter is abundantly silicate and aluminum and is less dense. Tectonic plates also collide with one another at the continental lithosphere. The continental crust is pushed upward, creating mountains and the largest masses of continental crust. To get close to the middle of the Earth as possible, one wouldn't want to start digging at the top of a mountain. The advantage of being at the continental crust is avoiding the trip to the ocean floor. Mantle. After getting through the crust at approximately 40 miles down, we would reach the mantle. The mantle is 1,802 miles thick and is located between the core and the crust and accounts for 84% of the Earth's total mass. The mantle is identified in 2 parts, the upper mantle, closer to the crust, and the lower mantle, closer to the core. Within these 2 divisions are their own distinct and interesting subdivisions. Scientists don't know much about the mantle as they do the crust, but we're able to gain insight about the mantle through seismic and volcanic activity. Scientists believe that when the Earth was forming, the heavier iron and nickel dropped to form the core. The lighter outer rocks formed a molten matter around the core, creating the early mantle. What do we know about the mantle, and what may we find if we one day dig a hole that reaches there? The upper mantle. The upper mantle begins at the lithosphere. This may be a bit confusing because the lithosphere is the actual area where the crust meets the mantle. But as a division, it includes the top of the crust into the upper mantle. The lithosphere, as it is the stretch where the crust and the mantle meet, is approximately 1832 degrees Fahrenheit and is separated by the Mohorovic discontinuity, called MOHO for short. It is located about 4.3 miles down from the oceanic crust and approximately 22 miles down from the continental crust. MOHO is the space where seismic waves change speed and accelerate, making tectonic activity. Beneath the MOHO in the upper mantle, beginning about 62 miles down and encompassing the area all the way to 255 miles down from the Earth's surface, is the asthenosphere. The asthenosphere is characterized by malleable flowing rock. The volcano's magma comes from the asthenosphere. At the point where the asthenosphere reaches 255 miles down, this upper mantle space is then categorized as the transition zone. At the transition zone, rocks no longer melt. At this location, the crystalline structure of rocks changes and they become denser. Extending in the range between 255 miles down to 410 miles down, the transition zone stops a large exchange of matter between the lower and the upper mantle, although some scientists believe that slabs from the tectonic plate can reach the lower mantle. What's interesting about the transition zone is that it is mostly made up of water crystals. Scientists theorize that water entered the mantle at the point of subduction in the tectonic plates. The bottom of the transition zone is about 410 miles from the surface and is estimated to be 2,912 degrees Fahrenheit. Those are some hot rocks. The lower mantle, 410 to 1,800 miles beneath the surface and above the outer core, resides the lower, known as the mesosphere, not to be confused with the mesosphere in the atmosphere. The lower mantle is more solid than the upper mantle. The extreme pressure in the lower part of the mantle makes it more solid, like clay. The lower mantle is graphed into 3 different sections. The uppermost section is 410 to 480 miles beneath the surface. The mid-lower mantle is 480 to 1,677 miles down, and the D layer is 1,677 to 1,800 miles down. The temperatures range from 3,068 degrees to 4,274 degrees between the upper and mid-lower mantle. At the core mantle boundary at approximately 1,796 miles down, the temperature is believed to be 6,692 degrees. If we could see inside the lower mantle, it would resemble a lava lamp, as convection waves send hot magma up into the lithosphere. The point which separates the lower mantle from the outer core is called the Gutenberg discontinuity. The core. Gutenberg discontinuity is described by its seismic waves at the core mantle boundary. Another theory suggests that the top of the outer core is thought to be up to 2,780 degrees hotter than the mantle just above it, which creates a thermal boundary in addition to the discontinuity found here. Because some elements found in the core are metals that dissolve in iron and are rare to find on the Earth's surface, are precious metals such as platinum and gold. The core is divided into 2 sections, the outer and inner core. The outer core is approximately 1,367 miles thick and between 8,132 degrees and 9,932 degrees Fahrenheit. The outer core is found from 1,800 to 3,200 miles into the Earth. It's composed of iron and nickel and is a hot liquid. The inner core is a hot, dense, solid ball made up of iron and nickel and is 3,200 miles to 3,958 miles beneath the Earth's surface. Though the temperature of the inner core is about 9,392 degrees Fahrenheit due to the immense pressure of the weight of the rest of the world, the iron in the inner core is not able to melt into a liquid state. After traveling all the way down to the very center of the Earth, we believe we'd find precious metals and a metal ball at the temperature of the sun's surface. Is there a reason to try? If we could get to the center of the Earth, what in the world would we want from there? There's a real benefit to geothermal heating and electricity. tapping into the geothermal gradient, which is the measure of increasing temperatures to the rate of increasing depth into the earth. We are able to heat homes by exchanging heat to and from the ground, using a pipe 6 feet into the ground. If we were able to safely dig further down, who knows what kind of technological advances we could achieve. The main reason why humankind digs further into the earth is to learn about the earth. Getting samples closer to the core would give us concrete information about how the earth was formed. We would have solid evidence of what the earth is made of, as opposed to uncertain evidence provided by a study of seismic waves. The Kola Superdeep Borehole is the furthest we've ever dug into the earth. The Kola Superdeep Borehole was created by Russian scientists with the intention of going as far down into the Earth's crust as possible. Located in the Arctic Circle, near the Russian border into Norway, the Russians were able to dig 40,230 feet, 7.6 miles into the Earth. The drilling began in 1970 and stopped in 1992 when the temperature in the borehole reached 356 degrees Fahrenheit. The temperature was more than the scientists were expecting at that level, and drilling had to stop. Scientists expected temperatures to be in the 212 degrees Fahrenheit by that point into the Earth. The actual temperature and decrease in density made drilling further impossible. The rock had a density almost like plastic, and the drilling ceased in 1992. In 2008, the Al Hashin oil well in Qatar dug just a bit further, down to 40,318 feet. So how deep could we possibly dig into the Earth? As of now, it doesn't look like science will take us even half the depth of the Earth's crust. But with improved technology and some future genius, maybe one day we'll have a more factual evidence as to what the world is made of. For now, theoretical and information gathered indirectly will have to do. I hope you enjoyed this video on how far we could possibly dig into the Earth. If you would like to see more videos like this one, please don't forget to like and subscribe.